Hello and welcome to Sarat Chandra IAS Academy, where your dreams are our mission. This is Yatharth here. So first and foremost, apologies for my brief absence. That was because of my ligament surgery in the knee. I am back now and we'll be continuing as usual. So today we'll be discussing about Aditya L1. This is a new mission by ISRO for the sun's study. As you all may be knowing already, Aditya means sun. Ditya means night or darkness, Diti, and A means the remover of the Diti, that is the sun. Okay, so let's see the basic. So Aditya L1 shall be the first space-based Indian mission to study the sun. The spacecraft shall be placed in a hollow orbit. So these are the things that we need to know, that what is a hollow orbit. Sometimes what happens that we read the news, we just miss out the important points, that what we should pick from this news, what are the pickups. So pickups are important from here. I have highlighted the pickups and we will be reading about them because they can come as usual into the exam, into the prelims especially. Alright, earlier also in 2022, one question came from the sun's waves. A solar storm comes and what will be affected on Earth. Alright, so these things can come. So hollow orbit around the Lagrange point L1 of the Sun-Earth system. So we need to know what is this Lagrange point. So in the Sun lecture earlier we covered, I told you that we will be reading this. So in this lecture we will be dealing with this. And Sun-Earth system also we'll cover because some fact can come from here directly into the prelims, that what is the distance, what is the time taken by light to reach, etc. So you need to know this. So which is about 1.5 million kilometers from the Earth. So what is the distance? This L1 from the Earth. Okay. A satellite placed in the hollow orbit around the L1 point has a major advantage. So why it is placed at L1? Because there is a major advantage. We'll also see what other space structures have been placed in the L1. So you can tell me in the comment section by then that where is this James Webb telescope has been placed. Okay. Is it L2, L1, where it is? So what is the advantage? That it will be continuously viewing the sun without any occultation or eclipses. We'll also see about the eclipses a bit. This will provide a greater advantage of observing the solar activities and its effect on space weather in real time. The spacecraft, this Aditya L1, carries 7 payloads to observe the photosphere, chromosphere, and the outermost layer of the sun, the corona. So please remember these things. Which is the outermost layer of the sun? It is the corona. Using electromagnetic and particle and magnetic field detectors. Using the spatial vantage point L1. So 4 payloads directly view the sun and remaining 3 payloads carry out in situ studies of particles and fields at the Lagrange point L1. So in situ means, just a second. So in situ, it means in the mother's womb. That means wherever the origin is. Okay, ex situ or in vitro is outside of this. So thus providing important scientific studies of the propagatory effect of solar dynamics in the interplanetary medium. The suites of Aditya L1 payload are expected to provide most crucial information to understand the problem of coronal heating. So this is also important, that what is this coronal heating? Coronal mass ejection. This is also important to understand pre-flare and flare activities and their characteristics. So question came from here earlier. Dynamics of space weather, propagation of particle and fields, etc. Okay, this is the structure of this Aditya L1. Just a second. Okay, this is the structure of this Aditya L1. So what I have understood from here and what I mean to tell you is that you should know at least the names of these things. See, SWIS, steps 1, Helios, Suite, and VALC, PAPA, Solex. So these terms you should notice once. Alright, what can come into exam is that Helios, PAPA, VELC, and Solex. Okay, so these are the parts of which of these following? Chandrayaan 1, Aditya L1. So whenever such diagram you see, you should at least check it once and read the name of these things. Okay. Okay, let's move further. what we see here is this is the sun. Just a second. Alright, so this is the sun here that we can see, and this is Earth here. So here are some points, or let's say gravitational orbits around the sun. Of course, sun is a very heavy object and its gravity will be pulling everything. So if something has to be here or orbit the sun, let's say, then its gravity must be balanced. So between the sun earth system, there are some points like this. So this is L2 point, this is L5 point, this is L4 point, this is L3 point, and this is L1 point. So we are talking about the L1 point. As you can see, the L1 point is located between the earth and the sun. Okay, here it is located. One more thing that you must understand is that sun is quite bigger than the earth. Let's say if this is sun, then earth is not even like this. Okay, not even like this. A tiny point. It's very small. So these are quite afar. The distance is a lot. Okay, it's not like how it looks here that they are located very close. So whenever you see the sun earth systems in the diagrams, please always take care of the scale. Okay, these things are not to be scaled, but just to give us an idea. Okay, let's move further. So what we see here are 4 points. This is L4 point, this is L1 point, this is L2 point, this is L5, and this is L3. So these are known as Lagrange point. So of course, all these points are stable points where spacecrafts or satellites can make their orbits. Alright, where things can remain stable. But all these points, L1, L2, L3, L4, L5, they have various different properties about them. Okay, so let us see about them one by one. So Lagrangian point or liberation point are point of equilibrium for small mass bodies. What are small mass bodies here? Let's say satellites or telescopes under the gravitational influence of two massive orbiting bodies. So what are two massive orbiting bodies here? This is the sun, and this is, second thing is earth. Okay, the earth is orbiting the sun. The sun is itself orbiting something, let's say another star, and it's also displaying a translational motion. So this can make Lagrange points an excellent location for satellite, as orbit correction and hence fuel requirements needed to maintain the desired orbit are kept at minimum. So just a second. So see, if by fuel expenses, a satellite can orbit anywhere in the space as it wants to. But we don't want to expend so much of fuel. We don't want to fight the gravity. That means, let's say in this satellite, it's orbiting, this is Earth. So Earth is also pulling this. Okay, and Sun is also pulling this satellite towards itself. So let's say if the orbit shrinks, then it will be pulled towards Earth. Then to maintain its orbit, it has to put some energy or fuel here. So we don't want to expend all this fuel. We want to maintain a stable orbit between both these bodies, and these points are Lagrange points. So for any combination of the two orbital bodies, there are 5 Lagrange points, L1 to L5, all in the orbital plane of two large bodies. So this is very simple mathematics, nothing else. Let me just do it for you. So let's say there are two masses. This is M1 and M2. Okay. So a third mass, if you want to put it between these two, where can it come? It can either come in between them. Okay. Either it can come here, or it can come on this line. It can come on this line. It can come on this line, or it can come on this line. Alright. So there are almost 1, 2, 3, 4, and 5 points. There are always 5 points for such mass bodies. You may have read in physics someday in the past. So basic physics, nothing else. So this can also come into your CSAT, okay? That for two mass bodies, how many points of equilibrium can be achieved? So 1, 2, 3, 4, and 5 points such can be achieved. So please take care of this. Just remember it as a fact if you want to. So two important Lagrange points in the Sun-Earth system are L1 between the Sun and Earth and L2 on the same line at the opposite side of the Earth. Both are well outside the Moon's orbit. Okay. So currently, this is a very important information. Just a second. Okay, so currently an artificial satellite called the Deep Space Climate Observatory, that is Discover, is located at L1 to study solar winds coming towards Earth from the Sun and to monitor Earth's climate by taking images and sending them back. The James Webb Telescope, a powerful infrared, please remember this infrared, okay? A space observatory is located at L2. This allows the satellite large sun shield to protect the telescope from the light and heat of the Sun, Earth and Moon. Very important. Okay, so we are not going to the L2, we are going to L1. This is L2, this is L1. Okay, we don't need to focus on L4, L3 and L5. We'll keep in the line of the Sun-Earth system. So L1 and L2. Okay. So due to the natural stability of L4 and L5, it is common for natural objects to be found orbiting in those Lagrange point of planetary systems. Objects that inhabit those points are generically referred as Trojans or Trojan asteroids. So this is also a very important term for exam. It can be asked in prelims that what are Trojan asteroids? Okay, earlier questions have come on neutron star, white dwarf, pulsar, asteroids, meteorites. So there is no wonder if question comes on this. What happens when question come on new things? Let's say in prelims 2024, question comes on what are Trojan asteroids, let's say. Okay, so assessors will tell you, okay, so UPSC is asking space sciences now. So please, whenever you are reading science, so please take care of these things also. So after that you will be reading, okay, so UPSC has asked, so let us read. So this is not the way. The way is to always keep assessing that what can be asked from here, what can be asked from there. So if ISRO is launching Aditya L1, so you must know about this L1, L2, L3, L4. Okay. So this can be asked directly. No wonder if it's asked in next year. So please remember what are Trojan asteroids, okay? And where are they usually found? They are usually found in L4, L5. Okay, let's say what are halo orbits. So halo orbit are like a special path in space where object can stay in a sort of cosmic balancing act. So this is simple orbit around the L1, L2 points. Okay, stationary orbit are halo orbit. In very simple, but let's understand a little bit more. So imagine you have a satellite that wants to hang out near a planet or moon, but doesn't want to crash into it or fly away. So when it needs to remain stable, okay, doesn't want to fly away or crash into it. So instead of circling directly around the planet, it follows a wavy path that keeps it roughly in the same spot relative to the planet. Because planet is also moving, okay? So it will also be in wavy path. These paths are shaped like a donut or a figure 8 and they result from the combined gravitational forces of the planet and the sun or other celestial bodies. So we need to figure out, there are many celestial bodies and every celestial body in the space must be having a gravitational effect on this body. Okay, so this we need to keep in mind. So halo orbit are like bit of finding the perfect spot where the pull of gravity from the planet and pull of the sun balance out, allowing the satellite to stay in a stable position without using much fuel. So what is the point that we can pick from here? That halo orbits are not always circular. They are wavy or like a figure 8. Okay, this is what we need to pull out. So this is about the L1, Aditya L1. So it will take from Earth, then keep rotating a bit like this and keep increasing its orbit, and then it will exit the the Earth system. It will come into the cruising phase. From cruising phase, it will now expend some fuel here because it needs to change its direction like this, and then it will go to this phase. Okay, around the L1. This is L1 vantage point. So here it will be halo orbit. Okay, so it will keep cruising here without expending much energy. All right. Let us also learn about the Sun-Earth system because this has come again and again into our lecture. And this is very basic thing when you read the geography, GS1, then you read the physical geography. then this is the first thing that you need to know about or learn about. Okay, please also remember that Earth axis is this. It's also little tilted, and this is Moon axis. It's also little more tilted. Okay, this all we taught already in the Chandrayaan lecture. All right, and this is the Sun. So Sun we'll keep in reference. So Moon comes between Sun and the Earth, and Earth is located here. So let's see. This we'll read a little bit later. All right. So Sun is a massive hot ball of gas primarily composed of two things, hydrogen and helium, which is hydrogen is more than helium. Trace amount of other elements make up the remaining 2%. And Earth orbits the Sun in an elliptical path, which takes about 365 days to complete. This direction you remember anti-clockwise from the Sun as center. Okay. So how is Earth revolving? Anti-clockwise, like this. Okay. So this orbital path is responsible for the changing seasons on Earth. Okay, seasons, not the day and night. And day and night are because of its own rotation. So here let's say is Earth. So this seen from North Pole, it is also revolving anti-clockwise, not clockwise. Please remember. All right. So Earth orbits the Sun at an average distance of 149 million kilometers. So just remember, let's say 150 million kilometer. Okay. Now what is a million? Million is 10 lakh. Okay, that means total of 6 zeros. So this is 1 million. We multiply it with 150. So 15 to the power 15 to 10 to the power 7. So these many kilometer. All right. So this is a lot of kilometers. So one complete orbit takes 1 year, sidereal year, during which time Earth has traveled 940 million kilometer. All right. In the prelims this time this word came, crepuscular. So which of these animals are active at both day and night? So we need to know this meaning of these things. Sorry, sidereal. Okay. So what is sidereal? Sidereal means the Earth year. Okay. Axial tilt, also called obliquity, refers to the angular planet rotation axis made with plane of its orbit. So Earth's tilt is 23.5 degree from its plane. Okay. Resulting in many remarkable effects, including the seasons around the planet. Now we will see its rotation. So first of all, what we saw? It's anti-clockwise. Okay, and Earth's own rotation is also anti-clockwise. So these two things you remember. This is when we are seeing from north. When seeing from south, this rotation will become what? Clockwise. Okay. When we see up from the south, it will become clockwise. All right, but let's not focus on this. Just take the North Pole as reference. All right, so when we see winters, or let's start from anywhere, the solstice also came in the prelims. When is the summer solstice falls? And the option was like last 15 days of this. Okay. So we need to see the equinox and solstice also. This is a summer. Okay. So light is on this. Equal light is on this phase. Okay, this is autumn. Then there are winters. Okay, this is spring. This is a change in seasons. Okay, this is because the North Pole right now is in towards the sun. And in the winter, this North Pole is away from the sun. Okay, completely away from the sun. So we base up our findings on North Pole. Okay. This is here autumn equinox, where both the poles receive same light. Okay, this is also an equinox. So vernal equinox and autumnal equinox. Autumnal equinox is September 22, 23. Vernal equinox is March 21, 22. This is winter solstice. Incoming solar energy greatest in southern hemisphere. So southern hemisphere will receive more light because of this tilt. Okay. This is summer solstice. So northern hemisphere is in tilt and it will receive more light. Alright, incoming solar energy greatest in northern hemisphere. And here it will be equal. That means equinox. From equal made equinox. Alright, so just remember the dates. Equinox dates are March 21, 22 and September 22, 23. All of them fall later in the month, like after 15th. Okay, this you must remember. So just remember the month, don't remember the date. Just a second. So no need to remember the date, just remember the month. That solstice months are 2. Summer solstice in June and winter solstice in December. And equinox months are 2, which are them? March and September. Okay, so just remember these. Okay, let's move further. Let's see two more things. That when we talked about the L2, sorry, L1, we said that there will be no eclipses. So L1 is here. So L1 is far from even the moon's orbit. This is Earth. This is, let's say, moon's orbit. And L1 is far from here between the sun. So here is sun. So this is the best place to directly observe the sun. There will be no eclipse or anything. है ना? So these are the eclipses. This is the moon. When moon is casting a shadow on the earth, then it is the solar eclipse. Okay, because the sun will be hidden because of this shadow. And there is lunar eclipse when moon will be hidden because the earth is casting a shadow on the moon. So these are two type of eclipses. One special question comes into our mind, that why eclipses are not present every month. Okay, if the moon is coming in front of earth every month during one rotation, then why eclipse is not happening every month? So the answer is hidden in the tilt. Okay. So this moon has this 5 degrees tilt in its axis. Alright, so this is Earth's orbit around the moon. And this is moon's orbit around the earth. So this is little tilted. 5 degree it is tilted on its own axis. And there is some tilt in the overall orbiter also. So this is why moon sometimes is below the earth. Okay, not directly in this line. And sometimes it above the earth. Okay, only few times it will fall between the this line where eclipses can happen. Okay, so this was today's lecture. I hope you learned a lot from this lecture. This is Yatharth here, signing off. I'll see you in the next video. Thank you very much. Have a good day and keep studying.